Great. So I'm Anna Dyreson from Michigan Technological University. This work is from when I was at the National Renewable Energy Lab in the United States. And so I want to thank the authors at the Renewable Energy Lab as well as Pacific Northwest National Labs. This work is looking at, as David said, the impacts of heat and drought on the Western US as very renewable energy adoption increases. So what I want to talk about is what are the power system impacts on kind of the transmission scale power system of drought and heat, and how does that change with very renewable energy adoption? What are the limitations of current models and data sets? Just for some context, borrowing here for this international audience, borrowing here a figure from a different publication, but showing the Western US and how, as folks probably know, we have different separate connections. So highlighting on the left side, the Western US, and just for a bit of context, we have hydropower shown there in the blue, a lot of hydropower in the west and northwest portions of the Western US, and then a concentration of population in Southern California in that red dot. So in this study, we were looking at the impacts of heat and drought on two different infrastructures, focusing on an operational timescale. We looked at two infrastructures, a low very renewable energy and a moderate very renewable energy, acknowledging that this moderate very renewable energy capacity is sort of a limited scenario, only 31% VRE, but that it kind of gives us some indication of future VRE capacity in the Western US. Oh, and I should say here, this is a recently accepted paper that I can cite in the Slack channel that will be out soon, and the authors there I want to thank are listed. So the heat and drought scenarios that we looked at in those two different infrastructures, we looked at the impacts of heat and drought on sort of a baseline scenario, and then we adjusted in isolation and in combination load, so the electricity load impacts of heat. We adjusted thermoelectric power plant capacity for temperature, and then we adjusted hydropower and thermoelectric capacity for water limitations, and then the combinations of all of those. So this sort of lays out those 5 different scenarios that we tested on the 2 different infrastructures. In this figure, I'm showing sort of the data sets and information flow, especially for this audience, noting that this was started with an observed meteorological data set. And so we did not use reanalysis data here. And what we did, I'll go into each approach in a little bit more detail, but basically on the temperature side, we used a stochastic model that generated extreme temperature years, where on the water side, we instead relied on that observed meteorological data set to select one historical extreme water availability or drought year. And then we adjusted the load, thermoelectric power plants, hydropower plants, and thermoelectric power plants for water availability, each separately and then together, finally to simulate those in an electricity grid operational model. And here we use a production cost model. So that kind of gives like an overview of the data flow, but I'll describe each of these in a bit more detail. For the electricity load, the baseline is shown on the left there. And so again, showing the Western US context. The resolution here is counties, so over 400 counties in the Western US is treated separately. And in our baseline for the low VRE capacity, which is basically a historical scenario, you can see how the load is separated, and the black and white image shows the concentration of load in the Southern California and basically the southern region of the Western US. The moderate very renewable capacity, so sort of the future-ish infrastructure, has a little bit higher load because that is it's approximate, but say it's a 15-year future, so it increases. Incorporates the effects of increasing load across the regions. So that's sort of the baseline on the left, and on the right is showing that what we do then, in order to study the effects of heat, we use this model which our co-author Naresh Shavanini created, which is a multivariate stochastic simulation model, and it takes the time series of historical gridded data and re-simulates those, kind of keeping the spatial correlations intact. He did that 100 times, and then from that, we selected a few of the more extreme cases to look at. In our case, we decided to focus on the Southwest US, since that's part of the Western US where the electricity load is highest. And we selected one extreme year to focus on in the paper that had a heat wave in that region. So that's what you're seeing on the right. The difference in load in what we call our extreme temperature year where the load increases in the Southwest US and those counties, the pink bar showing that the Southern California load is significantly higher, but the other regions are actually lower. And so that's just the case that we focused on here. We did test a couple of other, chose a few other of those 100 different simulated stochastic temperature simulations. And those are in the supplemental information, but I think one of them kind of tells the story for the most part. So we adjusted that electricity load as I showed in the previous chart. I should say that electricity load was adjusted with a regression model that's based on historical temperature sensitivities of load. For thermoelectric generators that are sensitive to temperature, which is most of them, we also adjusted their capacity. And so the figure on the left shows day by day, the capacity as a fraction for each generator type. Because of some assumptions we made, it happens that our gas combustion turbines and gas combined cycles have a pretty strong derating compared to nuclear and coal, which are steam cycles in general. So you're seeing basically you're seeing that summertime derating being very strong on the left-hand side there. And it is a daily derating because the base data, the temporal resolution of base data was daily resolution. So then on the right, you're just seeing for that one extreme temperature year that I'll focus on, how is that derating distributed and where the thermal capacity is. There's some pink there, and then darker pink or to red where the capacity was most highly derated. And we did do this derating in our case, incorporating the fact that plants that are designed to run in hotter temperatures should be less affected by the same temperature as a plant, say in the northern part of the Western US, where they're not designed for such a high temperature. So we sort of tried to incorporate that regional difference. On the hydropower side, as I said, we did begin with that same gridded meteorological data set, but then we chose 1 year, so 1977 is sort of a known drought year in the historical data set. And so we decided to focus on that year. And the way that our water side models work, and this is our colleagues at Pacific Northwest National Labs that lead this work, but we use the simulated distributed historical runoff and route it through a river routing model, and then take that through a water management model, which represents reservoir storage, release and withdrawals to meet other spatially distributed water demands, to give you overall availability of water for electricity generation at each power plant location. And so this map focuses on the hydropower piece and shows for each of those 400 counties, where was that hydro generation limited, where is that hydropower availability less than what we called our average year. A 2005 year was our base year. And so you can see that it's mostly in California where the hydropower is limited. Just for some kind of linkages to the electricity model, on the right is a graph showing the month by month availability for electricity generation in hydropower, where the blue line is the scenario is called water scenario, but it's our drought scenario. So you can see for each month, there's a different change from the base scenario. And how this linkage works is the monthly availability for electricity generation is passed from the water management set of models, of the hydrological models, to the production cost model, which then takes that monthly budget and optimizes how that might be planned for daily use. And then in the production cost model, which is a unit commitment and economic dispatch model, it can optimize hour by hour as it does a daily dispatch to use that hydropower along with all of the other resources. So for a real quick summary then, before I can dive into results, the scenarios as I described, there's those 5 different scenarios. A base scenario where we don't adjust any of these sort of stressors on load or hydropower or thermoelectric generation. A load scenario where we do adjust the electricity load. An air derating scenario, we'll just call it a derating scenario where we adjust the thermoelectric power plants for temperature. And then a water scenario where we adjust the hydropower and the freshwater dependent thermoelectric capacity. I guess I didn't say, I'll describe that quickly. For the thermoelectric capacity, we use a simple derating here. If they do rely on fresh water for cooling, we simply take their summertime capacity and derate that proportional to the summertime availability of water. So this assumption makes a pretty strong thermal derating for water dependent generators. And then the combination of all the scenarios is when we throw all of those things together, right, and do the combined stressors of load, derating, and water. So the figures on the bottom just sort of try to give you an idea of the resolution of these deratings and these various stressors. On the left is the load. We're going to focus our results on the summertime, and then particularly on 1 week in the summer where there's a heat wave that was in our simulated temperature data. And on the right, you're seeing the low and moderate, very renewable capacities. The top is the thermoelectric capacity. The jagged lines show you that when we do the air derating, it's on a daily basis. So you have a difference every single day for what's derated, versus the blue line, which is when you're only derating the water dependent generators, then it's a monthly basis, it's a seasonal derating. So it's one fairly significant derating, but over the whole season. And then the red line is for the combination of different scenarios when you have both water deratings as well as air temperature deratings. So that's the the 5 sort of stress scenarios that we implement on the 2 different infrastructures for a total of 10 cases that we'll present in the results here. What we find, then I just have a few slides that go through some key results. In the summertime, the generation is shown by source type on the top, and then on the bottom 2 graphs by region. So basically the drought has the largest impact on the simulated generation mix. This wasn't a surprise to us based on what happens in the real world, but also based on previous modeling exercises. When we have a limitation of the cheap hydropower or coal capacity, we're using more expensive gas combined cycle generators. So that's what you see in those drought and combination scenarios, is just really that strong effect of drought limiting our cheapest available generation. It's interesting just to compare those to the load and derating scenarios, where those scenarios are overall, when you look at the generation across types, or on the bottom, the generation across regions, there's just not as much of a change as the drought. So the drought really dominates those kind of large scale changes in generation mix. The other way to slice and dice sort of the same information is looking at the interregional connections. So here, instead of looking at the sort of the power flow between individual regions, instead we looked at each region and just said, was it a net importer or a net exporter over the course of the summer? So I should describe a little bit further, I guess. The first bar chart shows the totals. So you're seeing on the top, the regional imports. Southern California is a net importer, and it of course dominates the imports. I say of course, because if you know about this region, you know that Southern California is a huge electricity load and does import currently a lot of their power. So they drive the imports. Those come from exporting regions, which are shown on the bottom, which are a variety of different regions, but a lot of it from hydropower from parts of the Western US. So then the bar charts, the smaller bar charts inset there with the 4 different scenarios, show you that the change on the regional power flows or the regional interconnections is really dominated by a load instead. So when Southern California has that heat wave from our extreme temperature year, it will need to import more, and you can see that importing comes from a variety of different regions. Sort of no single player there provides all of it. Drought has an impact too, but the net effect of that drought is less. The load really begins to be more dominant. When you have both load and drought, then their combination effect is somewhere in between. One thing interesting to note here is that you go to the moderate VRE scenarios, which are on the right side. Overall, the amount of import is a lot less. And you can think about that. We use a fixed moderate VRE infrastructure, which I very briefly described, which had about 31% renewable energy penetration. That was from a previous study called the low carbon grid study for California. So it was really focused on California and increasing solar adoption in California, as well as somewhat across the Western US. So basically the import need is less because there's more of that solar built in region. So overall you need less imports, but when you have a load event, you still have to flex, right, to bring more imports in. The other way to look at those same results, or sort of those same effects, is by generation cost. So on the left, showing what we use here, again, is a production cost model. So it's optimizing for least production cost across the entire region. The drought scenario always increases our cost, again, because we're having to go to more expensive natural gas generation. The other scenarios don't make as much of a difference. The derating was, when you just look at the air derating alone, it doesn't add up to much of a change, and the load decreases our cost only because it was a Southern California focused heat event, where the other regions had decreasing load. So that's sort of the story on the left side, is that when you have any sort of drought event, it's going to increase the generation cost. But another way of looking at the same is on the right, looking at the unit cost per megawatt hour. You can see that the moderate VRE system has a lower unit cost, and that's just because it has that zero marginal cost wind and solar capacity added. So the unit cost is lower, and the regional interdependence is also lower in general. The x-axis there showing what is the total dependence of other regions on each other, and it is lower overall when you have a moderate VRE system, so that 31% variable renewable capacity or penetration. Then the final result slide, and this one is where I think it gets interesting, is to then look at what happens on an hourly basis. And this is really where a production cost model that we use, this is an hourly simulation, provides it more information than what a longer term or longer time scale model like a capacity expansion model would tell us. So here is showing that when we look at even though the summertime total of regional power flows decrease in the future system, power flows remain critical during peak periods. So say, for example, looking on the bottom, those are showing your diurnal pattern. So your hour by hour average on the bottom left is the summer average. The low VRE system sort of has a smooth profile following the load, basically. That's the total imports that are needed, up to 20 gigawatts, where the moderate VRE system has a dip, which is consistent with, the increase in solar capacity that might be generated in region. But you still need that 20 megawatts 20 gigawatts at the peak time. So even though you might say, oh, I'm less dependent on other regions, you still need that maximum transfer capacity. And on the right is showing during that peak week when we had our heat event, that heat event is really what drives this. So that 20 gigawatts is what happens when you have the load event driving those imports to Southern California in our case. It's the same in the moderate VRE system. So you still need to have that peak transfer capacity. And we thought this was interesting because in the real event that happened in August of 2020 in California, when there was a west-wide heat wave, and they had to do rolling blackouts in parts of California, the root cause analysis of that described that part of that was due to imperfect, I'll say, planning around those peak times and that peak need for transfer capacity depending on the solar generation and the net load, therefore. So some directions for research then. This kind of, to me, highlights the need for modeling frameworks that can handle both a large number of hydroclimatological scenarios and high spatial resolution and power system models. So the power system model that I gave this example of is fairly resolved, being 407 different counties across the Western US, having individual generator unit commitment and constraining the capacity at individual generators levels is fairly high resolution, but it becomes difficult just computationally to do also a lot of hydroclimatological scenarios. The next bullet point describes the need to explore the impact of the uncertainty in power system infrastructure futures. So of course, we only did 2 scenarios here, and I know that others have done work that do incorporate that power system infrastructure future and include a lot more scenarios for what future power systems will look like. But again, it's hard to do that as well as linking it to an operational hourly or sub-hourly model. And in addition, including scenarios that cover a range of climate futures. So we're seeing the challenge of incorporating all of these effects just computationally stacking up. And lastly, I didn't describe it much here, but one thing I'm very interested in, I should have said I'm an assistant professor in mechanical engineering. So my interest really in what are the underlying physical assets that are being affected. And Katerina talked a bit about that, but looking at what is the uncertainty and how we're modeling wind plant outages or electricity load increases or thermoelectric power plant capacity. And we sometimes just assume those models without thinking about what do we actually know, like how incorrect or correct are those models, or is there any single correct answer? So with that uncertainty in the physical asset models, that would propagate into this type of modeling or other multi-sector models. And I think that's an area of future work as well. Just give a quick along the lines of sort of that second takeaway point there. We have Stuart Cohen led a paper that just came out where we did link operational model to a capacity expansion model, which got at some of those future research directions that I mentioned, and that paper is now available as well. So thanks a lot. Happy to move to questions.